If you happen to see two little people running around, those are my boys. Apologize for the interference. All right, so yesterday we defined the line integral of a curve, and actually we defined three different line integrals. We did it only for functions, vector functions going into R2. So today we'll write down things for R3. It's not going to be any, there won't be anything surprising. Talk about space curves. So recall that we wrote down yesterday three different line integrals. All three of them for functions. F of x, y. So here C is some smooth curve. So remember, C is given by a vector function, r of t. Let's say A runs from t to b. And of course, every vector function can be written in terms of component functions. So this is x of t I plus y of t j. And we wanted only to look at smooth curves. So smooth meant that first it had a continuous derivative. So r prime of t is continuous. And then the second thing is that we didn't want it to ever stop. Right? Because remember, we were viewing this like a movie. And we didn't want the movie to stop, which means we didn't want the derivative to be zero. At least on this interval AB. Okay. So what were the three different integrals we wrote down? Well, two of them were easy. They're the ones that were just dx and dy. And then the third one looked at something a little different. That integrated over the arc length. So you took a space curve, or you took a smooth curve, and then you looked at intervals on that curve, and you computed their arc length for each of those intervals, and then evaluated the function at some point in that interval. And that's how you got this integral here. So that we wrote as ds. S for arc length. Okay, and then we had formulas for these. And these two were almost identical. They're both the integral from a to b, so that a to b is coming from the parameterization. And then you integrate the function evaluated at r of t, which means everywhere you see an x in your function, you put x of t. And everywhere you see a y in your function, you put y of t. And then you multiply by the derivative of the component function, x of t. And then multiply by dx. And the dy version is the same, only this gets replaced by a y, and that gets replaced by a y. To do the arc length version, well, in the beginning it looks the same. But when you go to multiply it by something, well, there's no s prime of t.
I think you're not supposed to put dx and dy.
Oh, this should be a dt. Sorry, of course. That's the whole point of changing it. So you have t's everywhere. Thank you. Now, over here.
Daddy.
Yeah.
I love my chalk.
It's up here.
Oh. I thought it was right here. All done.
So here, what you're going to multiply by, you take the derivative of r. So all of them take a derivative of something. But when you take the derivative of r here, you actually then take the norm of it. And then dt. So this bit, remember, equals the square root of x prime of t squared plus y prime of t squared. It's just the definition of how you compute the norm of a vector. Okay, so that's what we did yesterday, and these were our line integrals over smooth curve C. So today we just want to do all these same things, but over space curves. Okay? So, what's a space curve? It sounds futuristic, at least a little sci-fi-ish, but it's not. It's pretty boring. So, a space curve, C, is just going to be, wouldn't you believe, a vector function. All right, it's going to be the image in the plane or in space of a vector function. But now this should be. Oh, would you like me to open this for you? You want to say hello? No, you shy guy.
Daddy, take both of these oranges.
Okay, well, he doesn't need to eat that one right now. Okay, so here the plane curve has three components. And again, you let, say, t go from A to B. Okay, so this is how you can give a smooth curve. And again, we want the same conditions. R of t should be continuous, and R prime of t is not 0 on AB. So the image that you should have in your head of a space curve is, well, just imagine, I don't know, you throw a piece of string up into the air, and it's kind of floating down, right? And it twirls and whatever it is, but there it is. Okay, so you freeze frame, and no, you have a space curve. It's just in the air. Okay, it doesn't have to lie in one plane, which is what these planar curves over here did. That's why you might call them a planar curve, because they sit in a plane. What a shock. Okay, so if you have a function f that eats things on that curve and spits out real numbers, so c, of course, sits inside of R3. Okay, so it's a function of three variables. Then we define the line integral f(x, y, z). Right? And of course we could do it in we can do it the same way. We can do a ds, and we could do a dx, a dy, and a dz. And so you just define it as the limit as n goes to infinity, the sum I equals 1 to n, and then you have f of, well, we do the same thing as before, where we choose points on the curve and evaluate the function at that point and then multiply by arc lengths. It's the exact same definition, just with three variables. And of course, we don't ever want to have to compute this limit, so immediately we write down a better formula for it. And what you'll see is actually the formula doesn't change at all because of the way we wrote this down originally. This is again a to be f of r of t times the norm of r prime of t dt. Yeah?
The symbol between R3 and C is like belongs to?
Yeah, I'm writing it on its side. When you write
Oh,
this, it means it's a subset of,
okay.
but I'm just writing it vertically because that's the direction I was writing. So right off the bat, you can see one of the values of using the vector notation. The vector notation hides the fact that you have a function of three variables in here. Right? You could write this out in full if you wanted to. And you notice I'll start farther left. And this could be f of x of t, y of t, z of t times the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. And of course, if you had a four-dimensional one, you could write the same thing out, but you'd have to have, I don't know, a W in there.
Daddy.
Okay, just put it to the side. You could have a W there, and you have a W squared there. I mean, it just gets bigger and bigger and bigger every time. But if you use the vector notation, it's always the same formula.
I think,
This just hides the fact that you have a 4-dimensional vector function.
I need that.
Megan, how do you feel about that?
It's just a parameterization that I still don't really understand.
How do we parameterize something?
Yeah.
So let's pick something medium difficulty. It actually is easier in a sense, but it looks like it's harder.
Like, does it always have to be a line segment? Or can it be something else?
Parabola. Parabola is not a line segment, yeah. Okay. How do you parameterize this? Well, the line segment, it's in principle, it looks easier. But if you know a formula, an explicit formula, like y equals x squared, that makes parameterizing it very easy. So say this is the curve y equals x squared. A parameterization for this curve would be this. And we have to tell what x of t and y of t are. X of t will be t. Y of t will be t squared. And then you can let t be anything you like. So you could maybe let t go minus infinity to infinity, or minus 1 to 1. Right? Of course, if you did minus 1 to 1, right, it would go from here to here. And you would only do that segment of it.
So anytime you parameterize something, can you always make t go from 0 to 1?
No, for instance, not always. I mean, if you wanted a parabola, like the entire parabola, right, going off to infinity, this is much, well, I can't prove immediately that you can't. Yeah, assuming you're using the closed interval 0 to 1, then I don't think, and assuming you want it to be smooth, then no, you cannot use 0 to 1 to do the entire parabola. But when you're doing a line segment, you always can. Okay? And if you're doing any, let's say you just wanted to get it from minus 1 to 1. So an easy thing to do would be let t go from minus 1 to 1. When t is minus 1, that's when x is minus 1. Starts over here. When t is 1, ends there. But let's say, no, you really want to go from 0 to 1. Right? That's a requirement for you. Okay, this won't work as we've written it, because this, from t 0 to 1, it starts here and goes up. In that case, we can change the function, the parameterizations, to work. So for instance, let's see, how can we do this? So first, I would probably want to try subtracting 1 from here, so that when t is 0, this becomes minus 1. And then, well, we need to be trickier, because now when t is 1, it only goes to 0. So how can we do this? How about, what if we did like 2t minus 1? So now when t is 0, you get minus 1, and when t is 1, you get 1. So the x range would go from minus 1 to 1. Does that make?
Yeah, but for these purposes,
Of course, the y isn't right yet. But go on.
can you choose whatever time interval that you want to fit?
Okay. So this is a good question. So there you have to fiddle, by the way, with this, but this isn't so bad. 2t minus 1 squared, whatever the x is, you square it. Okay. So this would be a parameterization now. Your question is a good one because it brings up something I mentioned yesterday, which is if you change your parameterization, right, which is what we did here. We went to a completely different parameterization. You might expect your answers to change. Is that what you're worried about?
Yeah, I guess.
Then that's not what you're worried about. Anytime you use the word I guess, that's bad.
I'm not really sure what I'm worried about. Like, I glanced at the homework, and I don't know how to, like, make the C or something.
So here's the important thing. The line integral is more or less parameterization independent. What does this mean? This means, let's say I have this really nice formula for writing down the parameterization of a line segment. And it always goes from, t goes from 0 to 1. So you might think, oh, I always have to make my t go from 0 to 1. You don't need to. You can write down your own parameterization. Let your time go from pi to e plus 7. Whatever it is you want your time to go from. The value of the line integral is not going to change. Right? When I'm grading your homework, or whoever grades your homework grades it, or grading an exam, I don't look and say, ooh, yeah, technically that is a parameterization, but I don't like that one. That's not what happened, right? Mathematics says that I would be wrong. It doesn't matter what parameterization you're using. Up to a couple of things that you don't have to worry about. I mean, they're not, the functions I give are not going to be sufficiently interesting that where it's not independent it becomes really terribly relevant.
I find my book this on the ground.
Okay. So, as long as you can find a parameterization, then you're okay. Okay? So, the stuff that is very easy to find parameterizations for, line segments. Right? That's using that, you do the, let's say x1, y1. So, you take the initial point plus the terminal point minus the initial point times t. Okay, that's how you can do it for a line segment. Of course, you have to write it down a little bit differently to put the x's. Right here with the x's, it becomes x1 plus x2 minus x1t. Right, that's x of t. And y of t is y1 plus y2 minus y1t. So line segments, these are very straightforward. Circles, right? That's where if the center is x0, y0, and the radius is r, then I should write it like that. I should write it like. Then you get x0 plus r cosine t, and y of t is y0 plus r sine t. Okay, and by the way, in this first parameterization, t goes from 0 to 1. In this circle parameterization, t goes from 0 to 2 pi, not 0 to 1. But you could fiddle with it if you wanted to go from 0 to 1. And the third, that I don't have room to write down anymore, is any time when your function is given explicitly, in terms of y equals a function of x. You can always, if you have y equals a function of x, then you can set up the parameterization x of t equals t, and y of t equals f of t. Right, whatever the function is. And then you can let t be in any interval you like, just depends on how much you want. Right? If I want the entire parabola, it goes from negative infinity to infinity. Right? To whatever x values you'd be putting in. So that's 3 really easy ones to parameterize. And, well, I think at one point in complex I had you parameterize an ellipse. Okay, so, and that's not that's actually pretty close to the circle, little coefficient, but. Yeah, okay. So does that help at all? Okay. Okay. So nothing really interesting changed when we went to these space curves. Right? The formula, I mean, you do exactly the same thing, and if you keep things in vector notation, then the formulas are exactly the same, and it works again if I put z's here to have a function of 3 variables. So what I can do is add z's everywhere, and the formulas stay exactly the same. The only difference is that there's a missing formula. What's the missing formula?
Do you want with dz?
Yes. Give me dz. Give me the missing formula, Mr. Bond. Okay, so you could add that in. Everything is exactly the same except now you have z prime of t. Okay, so you can add that in. Okay, so this is not so bad. All right. So this exhausts what I want to talk about with integrating vector functions, right? Or I should say, not vector functions, but scalar functions over smooth curves given by a vector function. Okay, so I guess then we can talk a little bit about vector fields. Yeah. Okay, so what we want to do is try to mimic the definition of integration over a vector field, that is, over a scalar function over a curve, for a vector field over a curve. So let's see, what do I need? Let's let f be a continuous vector field. Okay, so over a smooth curve C. Okay, so let's remember, first, vector field, that means it eats points in space, right, or it could be in the plane, depends on if you have a two-dimensional or three-dimensional, and it spits out vectors in the plane. Okay, so it eats points and it spits out vectors. That's a vector field. Continuous, remember every vector field has component functions, right? You can write it as p of x comma y I plus q of x comma y j. And for a vector field to be continuous, that means that those component functions are continuous. Differentiable means that those component functions are differentiable. Okay, over a smooth curve C. So this C, of course, should be given by a vector function, r of t. So given by a vector function, r of t, where t goes from a to b. So the line integral of f over c is, so first we have a question of notation. What's the notation for this going to be? Note that another way that we wrote this down is integral over c f dot dr. That was another way that we wrote it. Did we? I can't remember if we wrote it that way actually. Maybe we didn't. Okay. Well, that's how we'll write this. So we're going to write this down. This is be our notation. You don't have to. This here. Really, you should think dot product. And this looks very strange. We haven't really sat there and talked about what do you mean by the dot product of this vector field with a differential of a vector function. And this is very strange notation. But to make this match up with what we're doing for line integrals, the way we're going to define this is it's going to be the integral from a to b, and then we're going to evaluate the vector field.
Excuse me, Daddy. I have to go.
You have to go, oh my goodness. Well, now that does make a difference. Okay, so just as we evaluated the function at r of t, we evaluate the vector field at r of t. And then we're going to multiply by the derivative of r. Okay, and we're not taking the norm here. Okay. I should say, this is really the dot product. And it's this dot product that's justifying this notation. You're taking here, you're thinking about this as the derivative of r, right, dr, with respect to t, should be r prime dt. So, f dot or dr means take this and dot it with r prime dt. Okay, so that's the justification for this notation. And I think there's two good reasons for having this notation. One, this is much shorter. Right, much easier to write down. And physicists have to use this all the time, so it's important that they not have to write all this down. The second reason is that if you saw this, if you had taken integral calculus, you probably could figure out what most of this means. You may not know what the dot product is, but you have a pretty good chance of being able to get pretty close. If you see this, you don't have a clue what's going on. So this is a good way of being elitist and stopping people from, outside the subject from knowing what you're doing. This is always important. Okay, so let's do an example. Okay, so what's my example going to be? So first I have to give you the vector field. This will be a three-dimensional one, and it'll just be x, y, y, z, x, z. All right, and the curve is going to be parameterized in the following way. X of t is just going to be t. Y of t will be t squared, and z of t will be z cubed. Oops. T cubed. And we'll let t go from 0 to 1. Okay, so if you projected this onto the xy plane, you wouldn't see the t cubed, but this would just be a parabola, right, going from 0 to 1. But the z of t, right, being t cubed, means that in the z plane, as you're doing this parabola, so let's say the plane was down here, so the parabola is going like this, from 0 to 1. Yeah? But now it's actually going up to 1 as it does that parabola. So it kind of looks, if you had made this wider, it would be a little slide that's curving in a parabolic arc. Okay? But it's definitely going down. Okay? Or, well, up if you're going this way, right? From 0 to 1, it's going up to 1. Okay, fine. So what if we want to integrate this vector field over this curve? Okay, we want to compute this line integral. We use the formula, of course, which is going to tell us we integrate from 0 to 1. That's what t goes between. Now we have to evaluate the vector field at r of t. So the r of t is given by x of t, comma y of t, comma z of t. So everywhere I see an x, I have to put in the x of t, which is t. Everywhere I see a y, I have to put in t squared. Everywhere I see a z, I have to put in t cubed. Okay, so my vector field becomes, okay, x gets a t, and then the y gets a t squared, so I get a t cubed. Yz becomes t to the 5th, and xz is t to the 4th. And then I need to take the dot product with the derivative of r. Okay, so r is t comma t squared comma t cubed. The derivative means I differentiate each component. So the derivative of t is 1, the derivative of t squared is 2t, the derivative of t cubed is 3t squared, and then we have 2t. So now you just need to take this dot product. So t cubed times 1 is t cubed, plus t to the 5th times 2t, 2t to the 6th, plus t to the 4th times 3t squared, 3t to the 6th, dt. And of course this bit here is 5t to the 6th. So this is a 4th t to the 4th plus 5/7 t to the 7th evaluated at 0 and 1. Oh. And at 0 they die. At 1 it becomes a 4th plus 5/7, which is 27/28. Okay, so that's the value of our line integral. Cool. Okay, so they're not hard to compute if you actually know what it means. You have to know that. I think I don't really. I kind of don't want to say this. It's really long and really boring. So let me give you the short version of it. I gave a derivation of this in my notes, but it's so long. And I mean, it's not. I mean, it's like this long on the page, but there's nothing. Everything is intuitive. Like the whole thing is, you're like, well, okay, yeah, this step, yeah, it's exactly what you do, and nobody would ever think to do anything differently. There's nothing interesting going on. So let me just say this: if your f is given by, say, p x y z I plus q of x y z j plus r x y z k. So these are your component functions. Then if you integrate the vector field over a smooth curve C, then this is the same thing as actually doing, well, there's three, it's really three integrals put together. Taking the integral of p over c with respect to x. So this is a line integral, and p is now just a scalar function, so it's what we did yesterday. Right? Plus, you integrate q over c with respect to y, plus you integrate r over c with respect to z. Okay, so actually, integrating a vector field amounts to integrating the individual component parts and then adding those up. And I want you to remember yesterday, this was special notation that we made up. Whenever I write this, it really means you integrate, you integrate, you integrate. Okay? But we shorten this out, and we don't want to write this down every time. So we just write it condensed like this. Okay, this is standard notation. I'm not making this stuff up. Okay. Okay. Well. Oh, is that clock a little fast?
Yeah.
Well, then I will give you the fundamental theorem before we leave for Thanksgiving, so that you don't have to wait all over the Thanksgiving break before you see the fundamental theorem of line integrals. But maybe, I don't know if we'll prove it. Okay, so what do I want here? Yeah. So let's let C be a smooth curve. Did I write curve behind me?
I heard a knock on the door, Daddy.
Okay. They can't have the room yet. So it's given by r of t. T goes from a to b. And we'll let f be a differentiable function. This is a scalar function of 2 or 3 variables. What I'm writing will be true for both. Yeah, Kevin?
This the fundamental of what?
I'll write it down.
Oh.
Yeah, then you can see it. So, fundamental theorem of line integrals. Now, you may at some point have asked, why is the definition of line integral we cooked up the right one? Okay, did I lose anything? No, I'm good. So what does the fundamental theorem say? Well, when you write down the fundamental theorem, it should convince you this is the right definition of line integral. Let's say you want to integrate over a smooth curve, and we want to integrate a vector field over it. And we're talking about a conservative vector field. So a conservative vector field, recall, means it comes as the gradient of some scalar function. So it means it looks like this set. Okay? For our f. So remember, this is the gradient of f. Okay, so if you integrate a conservative vector field over a smooth curve C, you can actually evaluate this. He's upstaging me. By taking the original vector field, f, wait, oh, sorry, like f, the function, and you evaluate it at the two endpoints and subtract. I think you're missing a 0 on the end. There you go. Okay, that formula should look familiar. It should look like another fundamental theorem. The fundamental theorem of calculus. Right? Just says if you integrate from a to b, function f, you take its antiderivative and evaluate at the endpoints, and then subtract those. So this is really cool because it's telling you that at least if there's nice enough stuff going on, and when we come back from break, I'll tell you what those nice stuff are. It tells you that this line integral only depends on the value of the function at the endpoints of the curve. Let's say you had two different C's. There's C1, and here's C2. I think you're missing a 0. The fundamental theorem of line integral says that if you integrate over C1 or over C2, what should the answer be? It should be the same because all you do is evaluate at the endpoints, which is kind of weird. I mean, this is really quite strange that only the endpoints should matter, that the path that you use to get there shouldn't really matter. Okay, we'll explore this in a little more detail next week, and I'll even give you an example where this doesn't work, so that we can see what kind of limits are on the fundamental theorem. But this is very nice, and this suggests to us that our definition was correct, because look, we got the fundamental theorem of calculus out. So we must be doing something right. Okay. Have a lovely Thanksgiving. Thank you for bearing with me today and my growing family. And have some turkey, tofurkey, turducken, whatever you like. Have a piece for me.